All right, folks. Okay. So welcome back again. Right now, we're going to talk about a different aspect, real-world Android apps. What do I mean with this? Well, last time, we actually checked about basic things about Android apps. And today, we're going to see more complicated things that real-world apps you often use. Okay. Why do we do this? It's a security class after all, not a developing class. Well, it's because malware authors actually use these complicated things to make the life of reverse engineering more difficult. Okay, so it's very important to understand what's going on and how these complex features kick in, because that's also what the malware guys are doing. Okay. That being said, also benign apps use them quite a lot. And once you have a sample, maybe you don't know if it's benign or malicious. So one of the key skills to acquire is to understand what an app is doing. And guess what? To understand what an app is doing, you need to be aware about these advanced features. All right. So let's start with app signing. It's a core concept in Android, and there is a lot of confusion online. So let's try to make this as clear as possible. I'm going to ask this at the final exam. Please, it's very important, and people get confused quite often. So eyes out. All right. So each app is signed with a certificate. Okay. So you basically compiled an Android app with Android Studio, and you get an APK. Well, this APK is already signed with a certificate by the Android Studio. If you're going to take this APK and you're going to unpack it, and then you're going to modify it a bit, and you're going to rebuild it, now the previous signature of this with the certificate is invalid, and you need to resign it with the certificate. We're going to see in next class how do we actually do this. Okay. What is a certificate, you may ask? Well, certificate is a public key of a public-private key pair, and it has some metadata identifying the owner of the key. Okay. And so the idea is that the owner of the certificate holds the corresponding private key. So this may not be very clear for you, and next slides are gonna try to zoom in a little bit, what this means with this public-private key pair and so forth. So if you did not get what I'm talking about right now, wait until 2-3 slides, and then go back to the slide and see whether you actually got it or not. And if you don't get it, just send me an email. Okay, I clarify for everybody. So quick primer on cryptographic signatures. The way it works is the following. Basically, I am the developer of an Android app, and I develop my own app, and then I also need to generate a public-private key pair. A key pair is a pair, so we have two components, and the first one is called the private key. We identify this with priv, and the second one is the public key, and identify this with pub. Okay. The idea is that the developer keeps the private key secret, while the public key, as the name suggests, is public. Okay. So again, we generate a pair, private and public. We keep the private for us, and the public could be, we can make it publicly available. Okay. Now, with these two components, the crypto people figured out that, hey, we can implement two very nice and very powerful primitives. The two primitives are the following. The first one is a signature. So the idea is that we can get a message. A message could be a string like hello, or it could be a string of bytes like an APK. Okay. And the idea is that given a message and given a private key, we can sign it, and now we have another stream of bytes, which is the signature. And the idea is that the name is signature because in theory only the developer who has the private key can actually sign it. Why is it the case? Well, if you check the primitive, sign primitive gets as input the message and the private key. Okay, since the private key is only available to the developer, only the developer can produce the signature. Okay, so that's one key component of this. The other primitive is the verify primitive. Verify, what does it mean? Well, conceptually, I take a message, I take a signature, and I want to verify that this signature has been generated by the owner who owns a given public key. So let me clarify a bit. If you check the primitive input to verify, there are 3 items. One is the message, one is the signature, and one is the public key. Okay, and the output of this step is valid or not valid. So the cool part about this is that the public key is public, so everybody can actually check whether the signature is valid or not. In fact, let's say we are in the context of Android security or Android, we have an APK. The APK comes with a signature. Okay, so the APK is the message and the signature is the signature. And as we'll see, this app also comes with a public key associated to this specific signature. So we have all the three ingredients that we need to verify if the signature is valid or not. Okay, so again, signature, only the developer can do it. Verify, everybody can do it. Okay, cool. And so the idea is that in the terms of, in the realm of app signing, basically, let me try to explain this. Basically, we say that the certificate does not need to be signed by the certificate authority. That's a very important concept. So I'm going to rephrase it a number of times, maybe with different terms, to make sure that you guys get it. So a certificate, as I said before, is just a pair of keys, private and public, and some metadata. Okay. Once you get the certificate, this certificate is literally just these things, but there is no certificate authority. Okay. So the apps, we say in Android, can be self-signed, and it's a major difference with SL certificates. It's a bit complicated because it assumes more or less you already have knowledge about this SL certificate and so forth. So again, some of these slides are a bit, self-referencing, or maybe to fully understand this slide, you need to get the following one. So my suggestion for this specific topic is try to see the slides and the presentation, and then after you did it maybe first time for these initial 10 slides, let's say, come back and try to understand if you get better what I tried to explain before. Okay, so again, you get a certificate, and the we don't have the concept of certificate authority in Android apps. What is it is going to be clear in a second, so be patient on this. The purpose of this app signing is not to distinguish, the purpose of this app signing is to distinguish app authors and not to identify them. So the idea is that you can distinguish between system and normal apps, and the idea is that the system apps are those that are signed with the system certificate, and that's how the system actually deals with the signature permissions that we discussed in previous slides. Okay, so again, let me try to go a bit forward so that maybe what I'm saying now is gonna get clearer. So an important part is that, again, the key point of these signatures, these signatures, is that you want to be able to distinguish app authors but not to identify them. Okay. What does it imply? Well, it implies that, for example, if you get a Facebook app and a Messenger app, you can check if they're signed by the same certificate. If yes, then you know that that these guys are signed by the same developer. Why? Well, only somebody with a private key behind this certificate can actually sign this. And since the certificate is the same in the Facebook and Messenger app, this is our assumption, then we can say, okay, behind this, there is the same developer. But pay attention, and that's the tricky part, by only checking the app certificate, you cannot determine whether the Facebook app you have is legitimate or not. Okay, so again, let's try to rephrase this. Facebook app, Messenger app, you know, okay, these are signed by the same certificate. You can verify the signature, it makes sense, through the verify primitive. And if it matches and the certificate is the same, you know that behind these two apps, there was the same person. But you don't know that this same person is actually the real Facebook company. Okay, that's an extremely important point. Now, in the web world, and maybe that's where the confusing part is, because maybe you have already heard about this certificate or certificate authority, is different. So, for example, if you go to Facebook, you're going to see something like a green lock. Now it's I think it's a black lock, but anyways, a lock. Okay, this means that your browser knows that you are actually talking to facebook.com, and then through this lock, you have the guarantee that you're actually talking to www.facebook.com. Okay, so how does the browser know that this is the real one? Well, in practice, what happens is that basically you go to the website, or the browser goes to the website, and the website presents, okay, this is my content, and it's signed with a certificate. And what the browser does is to check if this certificate is trusted. So he actually check whether this certificate is actually signed by another certificate, which is signed by another certificate, which is signed by another certificate, which eventually signed by a certificate that the browser actually trusts. So the way it works is that your browser has hard-coded a number of trusted entities. We call them certificate authorities. And in these trusted certificate authorities, basically it's the list of, if you are eventually signed by one of these certificate authorities, then you're considered trusted. If you cannot prove that there is a chain between your certificate and the certificate authorities, then I cannot verify that you are actually trusted. And so in that case, you are going to see like the red lock or some kind of scary red view. Okay. So before I go to the next topic, really the main difference is that in the browser world, in the internet world, you have this, you go to a website, you get something signed by the certificate authority, and usually there is a chain that brings you to one of these root certificate authorities, root CAs, that is trusted by your browser. Okay. In Android, we don't have this. In Android, we just have the app, the certificate, and the signature, and we can just know if the signature is legitimate and actually created by the developer with the private key associated to this public key. But it doesn't tell us anything about the public key. There is no chain that tells us, oh, this public key is actually coming from the real Facebook developer. We don't have this. Okay. I actually think I misspoke, a couple of slides before when I said that certificate as private key, public key, and metadata. Not really, in the sense that what you actually have once you get the APK with the certificate is the public key, of course, and the and some metadata, or like, the company that signed this and so forth. Of course, you cannot really trust the metadata. That's why even if you see in the certificate, signed by Facebook, well, an attacker can actually forge this. Okay, there is not the links this to the, that only real Facebook can create a certificate with the name Facebook. Okay, in the web world we have this because the certificate authorities actually sign a given certificate with the name Facebook only if it's actually coming from Facebook. But again, in the Android world, it doesn't happen. Sorry, I've been very repetitive here, but that's where many people fall. That's where there is a lot of misunderstanding. So I prefer to be very annoying that. But I really want you guys to actually get this. Okay, cool. Now, Android system actually builds on top of this concept, and it actually uses it a lot. It uses it a lot to implement some security features. For example, in Android, we have this thing called Android Shared User ID. That's something you can put in the manifest of your Android application. And the idea is that two apps can request to be assigned to the same Linux user ID. Okay, you can do this again by taking two apps. You specify in each of them Android shared user ID, and you specify which user ID you want to have in common. And the idea is that the system is going to grant the same Linux user ID to these two apps only if they're signed by the same certificate. Okay, so that's where all the certificate story actually kicks in. Okay, very important. If two apps happen to have the same Linux user ID, then all security barriers that we discussed thus far are completely gone. Okay, so two apps with the same Linux user ID share absolutely everything. From the eyes of the operating system, if you have two apps with the same Linux user ID, literally they are the same thing security-wise. Okay, it's like different processes belonging to the same Linux user ID. Okay, so both can have access to private internal storage of each other. Again, private internal storage is enforced through Linux file system permissions. So if you have the same Linux user ID, there is no difference from the eyes of the operating system. And both can access each other components regardless of the configuration. Okay, so the way you actually do this is something like this. These are two different apps, the manifest of two different apps, and you see package is different. So MOBISEC app 1, MOBISEC app 2, and Android share user ID, we have a string, that's the user ID, quote, some kind of identifier, and we put the same. Okay, if these two apps are actually signed by the same certificate and are installed on the same device, then these are going to be granted the same Linux user ID. Please do not fall for the trap of saying, oh, you know, this is only possible because the package name has the same prefix. No, it doesn't matter. Okay, this could have been MOBISEC 1 app 1, and this other one could be Peppa Pig. This stuff would work anyways. The package name, there is no weird relationship with them. There is no, oh, you know, since the prefix is the same, then some other security property applies. No, do not get fooled by this. Many people fall for this. Do not be one of them. Okay, the key point is to have this kind of meta thing in the manifest and being signed by the same certificate. Cool. Oh, sorry. Again, let me rephrase this. Both can access each other component. That's important, again, regardless of the configuration. So if you have two apps, and we've seen that an app, for example, can expose some functionality by putting exported to true in one of the components, it doesn't matter. Even if it's exported to false or whatever it is, the other app with the same Linux user ID, with the same, signed by the same certificate, is going to be able to access the same component. Because from the eyes of the operating system, these guys are the same security entity. Okay, cool. All right, another thing in Android are resources. Resources are something that are packed in the Android app. We're going to see next time how you can actually extract resources and analyze them. And the idea is that you put their files and static context. It could be like a picture, it could be strings, things like this that are used by the code. Okay, so we have different categories. Again, depending on the category, usually the files are placed in different directories under the resources folder. And you can have drawable, pictures and things like this. Layout, these are XML files that somehow specify how your graphic user interface of an activity, for example, should look like. Raw, some MISC files. And then you have another subfolder called values, which usually contain, static arrays or definition of colors. There I can put red is FF0000 or strings, okay? Let's have an example about strings. So if you open the strings.xml files of an app, you could see something like this. It's an XML file that specifies that, hey, there is a new string, we call it like this, whose name is secret string, and the actual value is juicy secret. The idea is that an app now can just refer to this meta, kind of name of the string and somehow retrieve the actual value of the string and use it in the code. Okay. This is used sometimes to, strings sometimes are part of some configuration thing. So depending on, you want to be able to change this and so forth. And the idea is that you separate the code with the actual configuration files. That's one of the good programming patterns. And again, the idea by doing this, you separate the logic and the code that deals with strings and the actual strings per se. So if you want to modify, for example, this juicy secret, you just modify it in the XML file without modifying any code. Of course, the idea is that you will keep this the same, but the idea is that, if you need to tweak this for some reason, you just do it without modifying this. And so the two things, code and actual string values, are left untouched. Now, let's say you have a string XML done like this. From the Java perspective, how can an app actually retrieve the value of a string associated with a given name? Well, let's check it out. You would find something like this. That's Java. So first of all, you do get resources. This is a method implemented, I think, in the context object. And usually, if you have an activity is a subclass of context. So even the activity object actually has access to this get resources method. So in your activity, basically you can do get resources. Now you have some kind of resource manager, and then on this you can call get string, and you pass as an input to this get string this kind of weird thing, r.string.secret string. That's interesting part because r.string.secret string, you may think that this maps to secret string. And in some way, it is true, in a sense that after you do this, the secret string is going to be juicy secret, okay? The interesting part is if you check the documentation of this get string, you're going to notice that the input for this get string is an integer, which is weird, right? Because we would expect that this is some kind of key value store, and from the key, we get the value. but here the input is an integer. How is it possible? And again, there is no trick here. So this getString documentation is this part. It's not that getString accepts even an integer of a string. No, this is actually the thing. So let's try to dig deeper. So if you check out this Java piece of code is actually ending up being in the Dalvik bytecode, in the, you know, the thing actually run on your device. And again, we're going to explore this in more details in future lectures. You're going to see something like this. They basically here, again, don't worry about the details about what's going on here. What you really need to understand is, hey, here there is some kind of invocation of a method, and then is invocation of get resources. And then on the output of this, which we store in v3, then we somehow invoke another method called getString, and we pass these weird numbers as input. See, we put these numbers in before, and then before comes as an argument of getString, and that's how we get the string as object, as a return value. Again, don't worry too much if you don't understand exactly what's going on. That's normal. We're going to figure it out later on. What I really want to show in this slide is there is no trick, in the sense that what you've seen in the previous slide, where somehow this r.string secret string maps to an integer, it's true. This thing actually maps to an integer, okay? And the question is, how does the system actually map this weird integer to this thing? Well, the way it works is that the system somehow generates another file that you can find in this public.xml, and somehow that's where the mapping is. So you're gonna see an entry, something like this, where basically this number is the ID of this name, and the name is actually this secret string, and that's where basically from this guy we can actually get the juicy secret. Okay, so I understand it's a bit complicated. This is going to be relevant where you need to reverse engineering some apps, where some apps actually use resources. And so in the code, you try to get what kind of string this app is asking to, and then you do, you can just see getString with some input number. Well, this slide shows you how you can reconstruct what the original string is. Go to this public.xml, find this kind of ID, try to find what kind of name this ID maps to, and then go in strings.xml and try to find which actual string value is associated with this string name. Okay, this is actually probably much easier to do than to explain. And next week we're going to have a demo on this kind of stuff. So I hope it's going to be clear there. All right, another thing that real-world apps use is runtime.exec. Runtime.exec, again, runtime is an object in Java and exec is a method. Is that you can think about is the analogous of the C system or Python OS system. So it's a way for a Java application or for an Android application to just call a shell command. Okay. So in C you would do system, ls or cat flag or whatever. Python is the same. Very, very similar in Android or in Java. Okay. You could have something like this, or basically you're just copying a file and put it in some other location through the cp shell command. Okay. Again, it's important because some apps use it, so you need to know what kind of stuff this exec does. Another very important thing that is used a lot by Android apps is reflection. So reflection is a Java interface to programmatically play with Java objects beyond what's normally possible. Fancy ways to say something not particularly complex, but what I mean with this is that if you just play with Java there are some limits. For example, if you have a field that is private, there is no way you can compile a Java program that tries to access directly a private field. Well, with reflection you can. What you can do is to just say, this field that was defined as private, well, change it. Change the access modifier, now I want it public, and then you can access it. Okay, so somehow reflection is a way to cheat a bit, to modify the core Java engine and to somehow bypass either some some settings or modify what's called the access modifiers. For example, if a field or a method is private, protected, or things like this, and so forth. Okay, you can also do things like you take a class and then you can enumerate what are all the methods that this class implements, or what are the fields that this class implements. And if you think about this, if you wouldn't have reflection, there is no way you can do this programmatically, okay? So if you have function foo with method peppa and method pig, then without reflection, there is no way that in one of these methods you can say, oh, let's get a list of all the methods of this class. With reflection, there is actually a way. So there are ways to just say, you know, iterate over list of methods, and you're gonna see as output method, you know, foo, method peppa, and method pig, okay? And this is particularly relevant because it complicates things a lot. And let's see how you call the pig method on the peppa object. This is very simple in Java. Well, you could do something like this. Don't ask me why for now, why somebody would do it. I just want to show you how you could use reflection to invoke a method pig of the object peppa. So what you can do is the following. You take the peppa object, you call this get class, which somehow gets a reference to the class, let's say, definition. Then on this, you can call get method, and you pass pig as string input. And this is gonna somehow get a hold of the, let's say, the reference of the method. And now that you have the reference of the method, so now that you have some object that somehow encodes, hey, this is the method that I would like to call, then you can do invoke, and you pass this object as first argument. This might be a bit confusing because pig is a method of peppa. Well, under the hood, what happens is that if you have a method of a class, the first object you pass is the reference to this object. So that's what's going on here. Once you have the reference to the method pig, you need to invoke it. It's a method of a class, so the first argument implicitly is this, and that's why it does m.invoke peppa. Okay, so that's how it works. That's what you can do with reflection. So you can invoke a method other than many other things. And the idea is that a malicious guy would do this. So before I said, don't ask me why somebody would do this. Well, if you're a malicious person, would you agree with me that if I need to reverse engineering, if I need to understand what's going on from here, it's quite clear. I'm just calling peppa pig on the object peppa. While if I have this could be a bit complicated. That's exactly what they do. And of course, they can do this multiple times, multiple layers. They could even call get class and get methods using reflection. So, you know, it becomes really an arm race where basically they can just go a layer deeper and so forth. Okay. So many of these things I'm going to show is more about, you know, there is a simple way of doing this, and there is a very, very, very complicated way of doing things. And in our mindset of security persons, we want to study this because malicious authors actually use these very complicated versions specifically to make our life more difficult. Okay, cool. Now, one could tell me that, oh, you know what, this is quite weird. Why wouldn't we have a rule that if I find something that uses reflection, we flag it as bad? I mean, this is clearly malicious stuff, right? Turns out there are many benign use cases for reflection. For example, one of the Google library, JSON library, it's a Java library that can be used to convert Java object into JSON representation, and vice versa. So you have this JSON string, so a string that is in the JSON format representing an object, and now basically you can map this to a Java class and access it with, you know, the Java syntax, like, you know, getting field and so forth. Well, this is implemented through reflection, because, you know, the fields that you have are depending on the JSON structure and so forth, and they cannot just have a Java class definition. They need to improvise and create fields on the spot and so forth. Okay. Or for example, if you have a class and you want to convert it to JSON, you need some code to enumerate all the fields you have. How do you do this? Reflection. Okay. So that's just to say, reflection sometimes is a sign of maliciousness, but it's not necessarily one. And that's what makes our job as security people, when we need to distinguish between benign things and malicious things, more difficult. So I want to dig a bit deeper on this kind of, you know, why the malicious people actually like this so much. Again, let's go back to the example Peppa Pig. And now we are here with this, you know, the reflective way of calling Peppa Pig. The key point is that, you know, if you have something like this, you could still somehow understand, okay, I'm calling the method pig on the object Peppa. okay? The reason why the bad guys really like this is that it's a string, and strings are very easily obfuscatable, okay? String can, I can just store some kind of, something stored with something else, or, encoded in base64, and then I decode base64. A string can actually come from the internet. So basically the string is not there in the app. I just go on the internet, grab a string, and that's a string that somehow tells me which method I'm calling. So in Java, you cannot do this, right? If you just have Java and you want to call pig, you need to put Peppa Pig as a method invocation in the actual code. So the reverse engineering would actually see this guy is calling Peppa Pig. Instead, if you use reflection, you can somehow improvise, and you can take this, the method you want to call from somewhere else, maybe even runtime, so statically it's not there, and of course it makes our life more difficult. Okay. So again, there is this pattern that malicious people sometimes they use somehow complex Java features that allows them to use strings. And why they do this? Because strings are very easy to obfuscate with respect to Java things like Java syntax and so forth. Okay. Again, it's a pattern. You're gonna see this multiple times. Another example of this is dynamic code loading. So what is dynamic code loading? Dynamic code loading is some kind of let's say pattern or functionality in which an app can somehow load additional code at runtime. So the code can be loaded from the file system. So basically you start the app, and then this app doesn't have the entire code base, but basically somehow, maybe in a file somewhere, like in the assets, in the resources, somehow reads this file, and this is interpreted as code, and basically the code, the execution flow jumps there. Okay, so this is very powerful because if the code is embedded in the app, okay, if you take the app, you somehow try to understand, okay, this app is reading this file, which is in the app, and then is using this as a code, and then it jumps there, you still have a chance to understand what's going on. But think about this. This piece of code doesn't necessarily need to be within the app. It could come from the network, for example, okay? So it could really be that you have an application that somehow takes, starts, and then goes on the network, grabs another piece of code, downloads it, and then executes this one. And this makes your life very difficult because if you just take the application and you try to look at it or what it does, you don't have full information, okay? Again, one problem is that, you could say, oh, well, this sounds very bad. Why don't we flag as malicious all the apps that use this? You cannot do this because benign apps do these tricks as well. So the mere kind of using of dynamic code loading is not enough to distinguish between benign or malicious, okay? So some use cases of why benign apps actually use this is for A/B testing. A/B testing is this kind of software engineering pattern that somehow, you have an application and then you somehow code a new feature, but you don't, you're not super comfortable and confident about this feature, and you want to have only a subset of your users to actually try this feature out so that you can get feedback. Let's say if they complain more and so forth. And in A/B testing, what happens is that you somehow deploy this change only to a subset of the population to then collect feedback. And then if this is successful, then you deploy to everybody. And sometimes applications use dynamic code loading to implement this feature, where basically an application grabs another version of a piece of code with a new feature and loads this, but depending on, if you are user X, yes, otherwise no, okay? So that's what happens in practice. Some other times they use dynamic code loading as a sharing, as a mechanism to share common frameworks. So in the past, we did a study on this, and we found some applications somehow relying on the existence of another application installed on the device, and somehow these other applications were trying to load this base framework from this core central application and somehow use it. And the idea is that you would install this core central application only once, and then you have all the other apps built on top of this framework which do not contain a replica of the code, which was quite huge. So you have framework X, and then you have app A, B, C, D, and framework X code base is not included in A, B, C, D. these guys are just hoping that the application is there. If it's not there, the app will say, you know, you need to solve application X first, so please do this, and so forth. How do they get from app A the code of X? Dynamic code loading. Okay, that's another example. The last example I have here is when you, for example, have games and you can play level 1, and then they would download level 2 only after you win level 1. And how can they run code that they just downloaded? Dynamic code loading. Okay, so in the past we found these apps where basically, you know, you would just have some part of the game in the application itself, but the other parts would be downloaded later on. Okay, cool. So again, these are benign cases. So if you cannot just grab and find dynamic code loading malicious, it could still be a benign functionality. Now, in recent years, Google tried to be more rigid on imposing that, oh no, you should not use dynamic code loading. So if I remember correctly, in the latest, not the term of service, but in the Google Play Store policies, there is written you should not load code from the internet and so forth. So for A/B testing, now there is a framework from Google. So on your Play Store interface, as a developer, you can say, please deploy this version of the app only to this subset of users and so forth. So somehow Google tried to implement these things so that apps don't need to use dynamic code loading. But honestly, I'm not sure how much this is enforced. Last time we checked, it was still possible to get an app that was dynamically code loading, dynamically loading code and so forth. But keep an eye on this. It could be that in the future it could be a violation of the policy. Of course, violation of the policy doesn't mean that it's not possible to actually do this. Okay, as we'll see next time with native code and so forth, there are many ways to bypass this kind of Java restrictions. Keep this in mind. Okay, again on the pattern of why malicious people actually like this kind of stuff. Well, first of all, because the code may not be in the APK, it could be from somewhere else from the network, but also because once again, there is an opportunity for the bad guys to use strings, and strings again are very nicely obfuscatable. So for example, that's how you concretely do class loading. So you somehow get a path of your file, you somehow use this desk class loader object, and somehow then you do this. Once you have the class loader, which is a class that allows you to load other classes, you can call this load class and you specify the name of the class. In this case, com MOBISEC Peppa. And once you have this, then you can call method pig. This is the same code that we've seen before, Peppa Pig, rewrote in terms of dynamic code loading. Okay, and again, nobody forces the attacker or the bad guy to keep the string in clear. Because if I show you this, you can tell me, yeah, okay, this guy is calling pig on top of com MOBISEC Peppa object. But of course, it's a string, so it could be obfuscated, encoded in some way, downloaded again from the network, and so forth. Okay, so again, there is another venue for the bad guy to, confuse you. And again, here there is a link to the paper I referred before. Again, it's a study from many years ago, from 7 years ago now. And that's where we try to start to understand, malicious apps keep using dynamic code loading a lot. Google is trying to stop this, but, at least at the point the policy would allow it. And we found out that they need to allow it because there were many benign apps actually using this kind of stuff, okay? I have many links of this kind, like papers and so forth. Check them out. I'm not going to ask you in the final exam or in which paper this was discussed and so forth, so don't worry. It just, if you're curious about how what I explained fits in the bigger picture of security research and so forth, you can get an idea. This is the kind of paper I've been working on for a while, okay? The last topic I have on this real world things is serialization. Now, serialization is something that is not specific to Java. And to explain this, I actually have a piece of Python code. So let's consider this class in Python. Very basic class. You have class Peppa, and then you have a constructor. We just take to initialize like an integer and a string. And then I have this method called pig that just returns a string repeated multiple times. Okay, very easy. Serialization is the process of, taking an instance of this class, let's call P, initialize with this n42 and the string chow, and somehow convert this instance in a string of bytes. In Python, you would do this like, for example, there are many ways. One library is called pickle. You can do pickle.dump p. You're gonna get something like this. Why would you do this? Well, the idea is that you want to take this instance and you want to translate this in a series of bytes. This is the process called serialization. With the idea that maybe we can send this string to another component. So for example, let's say that I have component X and component Y, and component X is access to this instance of the object Peppa. And let's say that I want to send this instance to component Y. Now, these things cannot just communicate by speaking. Hey, you know, what's up, dude? I have this object Peppa, and these are the N, and it doesn't work this way. So what usually happens is that there are some kind of IPC or inter-process communication mechanisms or some ways of mechanism. Again, if they are on the same device, it could be, you know, you write on a file and then the guy reads from the file, or some kind of intent-based mechanism that we checked last time. Or it could be that these components are on different servers, so you could want to send this instance through the internet and so forth. To do this kind of transmission, you need to convert the instance in a series of bytes. And so serialization is just this. You take an instance and you want to convert it in some way or another in a string of bytes, and string of bytes are nice because we know how to send them. We know how to send bytes over the network. We know how to write bytes in a file and so forth, okay? Now, pay attention, don't be confused. This serialized version of the instance encodes details about a specific instance of Peppa. Okay, so for example, there is written, you know, this instance of Peppa contains N42 and the string is chow, but it does not encode the actual definition of Peppa. This is very important. If I just give you this, there is no way, without guessing, that you can reconstruct what's going on here, okay? So please really try to understand this difference. One thing is the definition of the class Peppa. One thing is the serialized instance. This is just saying there is an instance of class Peppa and these are the numbers, but it doesn't tell me anything on how the class is actually structured, okay? And that's why if you try to take this string and if you try to call pickle.load of this guy, if your Python project or Python file doesn't have the definition of this, so if, for example, if you take another file, you try to load this from another Python program, you try to load this thing from a file and you do load on this, it's gonna crash. Why? It's gonna say, oh, you know, I'm gonna deserialize an instance of the class Peppa, but I have no clue what Peppa is, okay? So the way to do it is that first you import the Peppa definition, so it could be from module import Peppa, or you can copy the class Peppa in your file, and only then you can do deserialize this thing. Only then you can do pickle.load the string of bytes, okay? So again, this is what I just said is this. So to load the instance of Peppa from the raw bytes, your code needs to have the Peppa definition within the visible classes, okay? Otherwise it's not gonna work. Question could be, how is this relevant to Android apps? Well, you guessed it. Deserialization is very more generic. It's not only for Python. It's a generic computer science concept. And in Android, we need to use deserialization a lot. You remember when I said, you know, you may have two different components. They may want to send something around. Well, this could be two activities, an activity of a service or an activity of an app A and an activity of app B. We send things around through serialization. Let's try to dig a bit deeper. So once you send an object to another activity, maybe to an intent, what happens under the hood is that this object needs to be serialized before are sent via binder, okay? And so once you have an intent, once we build an intent, we put something in and we want to send it, what's going on under the hood is exactly what I'm saying now. First of all, you take this intent and you serialize it. Now you have a string of bytes. And now you can take this string of bytes and you can send it through, for example, binder. Okay, and the receiver is going to take this string of bytes and know, this, for example, contains an instance of class Peppa. The receiver needs to know about class Peppa, and if he knows, bam, as output you have an instance of class Peppa, and then you can use it as normal Java stuff. Okay, after this you can call pig. In Android, there are, this serialization again is a computer science concept. There are many different implementations of this concept. There are two main interfaces. The first one is parcelable, and the second one is serializable. So parcelable is the one actually used by Binder. So it's a you have an object, and you can say this object implements the parcelable interface if and only if there are methods that allow for writing this object instance to a parcel, which is another object, and reading from a parcel, okay, and create back the instance. And then the trick is that the binder knows how to send around this parcel. So somehow this parcel is already some kind of string of bytes, all right? And in Android there is also the serializable interface. This is more generic. So this parcelable is somehow more optimized for intents for binder transmission. This serializable is the more traditional serializable interface for Java. There is a nice tutorial in this link. What you need to remember from this is that components need to talk to other components. The way they talk is not magic. They need to somehow transform what they want to send in a stream of bytes. The way conceptually, the way you convert an object in a stream of bytes is called serialization. Again, this is a concept, it's not Android specific. And in many cases in Android, this happens under your eyes and you don't even notice. If you send an intent around, that's exactly what happens. You are somehow serializing your intent, and then the receiver is deserializing it, okay? All right. That's all I have for these real world things. And then next time we're gonna move on different topics. Ciao.